Alright. So the last class we learned chapter 3. Alright, which is under week 7, where you need to cover the integral form and the buoyancy. And this part, alright, this one under chapter 3, which is the introduction to fluid motion, we have covered as well. Alright, this part, what we have learned is about the characteristic of fluid in motion. So when we look at our surrounding in nature, we always deal with the fluid in motion. For example, wave, alright, it always in motion because of disturbance. What are disturbance? Might be from the wind, alright, might be from the human disturbance. So all of this disturbance will create the fluids in motion. So we learned about the description of motion. It is under Eulerian and Lagrangian, right? So for this tutorial, what we have learned in the lecture, I try to recap back so that by understanding the theory as well as hands-on practical, it will accelerate more on your understanding. So this part we will cover about this tutorial description of fluid motion for the acceleration. Okay. I hope you can see my screen. Alright, so you can see my screen, right? So the last part we learned about the fluid in motion. So this is where in the motion we need to involve velocity, acceleration, angular velocity, vorticity. So all that term actually refer to the motion. Alright, so what are the motions? So the motion refer to the fluid in motion. So this is actually we start with the velocity. The last lecture we learned about velocity. Remember, velocity is a vector quantity that contain the magnitude and the direction. So U is the magnitude, I is direction in X, Y, and Z axis. Alright. So by derivative of velocity with respect to time, we get the acceleration. So this is the formula of acceleration coming from velocity. So you notice that in the velocity term, all right, this acceleration, there is the space component. This is X, Y, and Z, and we have the time component. So combining space and time, that means we under Eulerian description. Alright, Lagrangian only refer to time. Eulerian refer to space and time. So we have space and time. So in this part, we're going to study and understand each term very carefully. So when the question asks a few parameters, you will identify what is the value of U, P, and W. All right. So you need to remember and understand the formula given here. So this is definitely acceleration in terms of U, V, and W. This is capital V. This is the we call as a total velocity vector. Remember, we have a difference between capital V and small v. Remember, this is capital V for the overall velocity vector. This small v refer to the y component, vector in y component. This is the velocity vector refer to x component, and w refer to the velocity vector in z component. So x refer to u, y refer to v, small v, yeah, not capital V, and z refer to W. This is magnitude of velocity. Alright. So let's take a look about one example. Okay. This is an example. Okay. Let's try to work out on this. Let me open OneNote. Right. Okay. This is tutorial. Hydrostatic stability. Alright, this under chapter 2. Okay. Chapter 2. Sorry, chapter 3. So let's take a look about this question. Alright. So the question is, a velocity field. The question is, the velocity field in particular flow is given by, this is capital V, remember? Capital V equal to 20y squared I minus 20xyj meter per second. Calculate the acceleration, right? This is the question. Acceleration, angular velocity, omega, vorticity, vector, and non-zero rate strain component at point 1, -1, and 2. So here is the question. This is basically the standard question. So the first step, right? Right. So the first step, please identify the question. Calculate. I try to highlight, calculate the acceleration, angular velocity, vorticity, and non-zero rate of strain component. So how many questions? We have 4 questions type. So we need to find the acceleration, and we need to find the angular velocity, which is omega. We need to find the vorticity, which is, this is symbol of vorticity, this is symbol of angular velocity. And last but not least is non-zero, all right? Non-zero rate of strain. What is the symbol? Is epsilon. So we have 4 questions. So the first part is we solve the acceleration. Right. The step number 1 is, remember we have derived previously the acceleration, which is using the equation, right? Using equation that we have learned previously, chapter 3, subchapter 2, number 9, which is acceleration refer to, that consists of space and time here, u partial derivative of capital B over partial derivative of x plus b, this is small b, partial derivative of capital B over partial derivative of y plus w, partial derivative of v, capital V, over partial derivative of z plus, last but not least, partial derivative of capital B over t. Right? So this component, you refer to the velocity field in a particular flow is given by this one. Calculate the acceleration. So here, we consider it is a steady flow. there is no fluctuation flow. So we can cancel the terms of time. Alright, when it is normally the case is steady, we consider as the differential of t is equal to 0. And then you can see this is a component of velocity vector. So velocity vector is equal to 20 y squared I, alright, minus 20 xy j. So from this velocity vector, we have to distinguish. Alright, so I refer to, remember we have previously, we have V, this is the formula. U, I plus V, J plus W, K. So that U refer to, so you can say that U refer to 20 y squared because I with I, alright, J with J. So V, small v equal to negative 20 xy. So W. So what's the answer for W? Please comment there. Do you know what is the value for W? Alright, Lim said 0. Alright, so definitely there is no component. We can say is 0 because there is a W there. You can see plus 0 W. Sorry, not 0 W, but 0 K. 0 K component. There is W component, but the W is 0. Okay, you can say W is 0. So from this value, you have to input all those value into this equation. Alright. Okay. So let's start with acceleration. Acceleration, by the way, if you have any question or any doubt, please feel free to comment there. Alright. So acceleration start with U. Where is U? Which is 20 y squared. What is delta V? Sorry, this is partial derivative of V over X. So V, this is V? We are going to use this V? Anyone? Are we gonna use this V? This is capital V, the total velocity vector. This is velocity in Y component, right? So remember, our velocity here refer to this velocity. This is capital velocity. So velocity here, we differentiate in terms of x. So from here, you try to differentiate. This is not in terms of x, so it become constant. You differentiate constant, become 0, right? And here, that means you differentiate one by one. You differentiate becomes 0 because there is no x component because you differentiate in terms of x. So you go the next part, negative 20 xy, you differentiate in terms of x. And then what do you get here? Do you get 0? I don't think so because negative 20 xy, you differentiate in terms of x, you will get negative 20y. Alright, Amirul Hakim understand, Afiq Rohaizam understand. Okay, if you understand, then you can comment there because I want you guys to learn together. We participate together, alright? So we get here negative. Okay, make sure bracket because you replace the value. Negative 20 y, this is j. Alright, because acceleration is a vector, we have the vector component j. Alright, this one is no need. right? You can delete it. This is not required anymore, right? And then next is plus v. Okay, plus small v, which is negative 20xy. And differential of v with respect to y. So you have to differentiate the whole this with respect to y. So you try to differentiate one by one. So you differentiate 20y squared. This go to the front, 40. Alright, become 40 y. Okay, and then you this one I. Make sure leave it I component. And then you differentiate here in terms of y become negative 20 x j. Alright. So from here, right, remember that w is equal to 0. So this term basically cancel equal to 0 because when you substitute w equal to 0, this whole term becomes 0, right? So from here, you need to simplify the equation. All right. So 20 multiplied with 20, 400. Y cubed. Remember, we have negative. All right. This is j component. And here, negative 20 multiplied with 40 become negative 800 x y squared I component, and negative become positive 400 x with x the power of 2 y. Alright, this is j. And then you simplify further with I there is no friend. J with j, there is a friend. So this one, you rearrange the equation. I, the first term, which is negative 800 xy squared. I, and this one, j, right? You can say that negative 400 y cubed j plus 400 x squared y j. So you see j and j, you see 400 and 400, you can factorize. All right, you simply factorize negative 800 xy squared I negative, you factorize negative 400. Once you factorize this also factorized by negative. So positive will become negative, right? This become y cube minus, because minus will get positive, x squared y, leave it j behind. All right. So this is actually step number 1. Step number 2, you need to, you need to substitute. All right, step number 2, you need to substitute. Sub the point given, which is 1, negative 1, and 2. This refer to x, this is refer to y, and z. So you substitute in this equation. So acceleration is equal to negative 800. X is 1, y is negative 1 squared. This will become positive later on. This is I, negative 400. Y cube refer to negative cube, negative 1 cube, minus x squared refer to 1, and y refer to negative 1. So basically negative become positive, positive 1. So this one, negative 1. So this term basically equal to 0. So this cancel becomes 0. Leave it only the I component, which is negative This is negative 1, the power of 2 still become positive, and leave the answer is negative 800 I meter per second. The power of 2. Therefore, that is the final answer. Alright, so far do you guys understand how to get the value of vectors, acceleration vectors? Alright, Amirul Hakim understand. Thank you very much. Anyone? For those understand, please comment you understand. Right? Okay, thank you very much. Alright. So for those still unclear, after this, please look at my video. Next. Alright, next, the question, find the omega. This omega is like an ear omega, alright? This omega is angular velocity. So you need to find the angular, right? Let's say this is B. Okay. So next question, find the omega, angular velocity. So remember that previously we have learned the angular velocity consists of a few components, which is angular velocity in x direction, y direction, and z direction. So previously we learned the angular velocity in terms of x direction, y direction, and z direction. So this direction reflect to your right hand rule. Right hand rule terms. For example, this direction, this is x direction. Your thumbs pointing to the x direction, but your finger curling toward this direction. Right? So this we call the positive x direction with respect to your thumbs. So you can try on your own, your thumbs curling, and then your finger curling, and then your thumbs up. So this is considered as a positive angular velocity. So we have derived previously the angular velocity for x direction is equal to the average velocity of two perpendicular lines. Remember our perpendicular lines A, B, and C, D. So this one you don't have to memorize. You need to understand. So this is the formula. Okay, I try to write it out. This is small v, Alright, equal to 0 because we consider it is static. So remember, our W component is equal to 0. There is no W component, 0. Is there any Z component? You can see this vector. This is only X and Y component, I and J. There is no Z component, which is K. Remember? So definitely we cancel out. So the angular velocity for the X component equal to 0. How about the angular velocity of Y component? Which is 1 over 2. And then partial derivative of V, small v over partial derivative of X minus U over Y. So you can see. X, Y. Alright, sorry, this is for Z. Let me delete that. Okay. Alright, this is Y refer to partial derivative of U over partial derivative of Z minus partial derivative of W over partial derivative of X. So when you look at here, in terms of Z, definitely there is no component, 0. In terms of W, there is no component at all. So we can cancel 0. So we can say that angular velocity in X and Y direction is 0. How about Z? Let's take a look. Is that 0? Right, so 1/2, this is average in terms of Z. Sorry. In terms of V, small v over the partial derivative of X minus U over Y. So we can say that angular velocity in Z direction is delta V over delta X. So we have the V component, the small v. Remember we have V. Yes. And we have U component. This we have. So we have the position in X component. Yes, we have I, and Y, we have V. So the angular velocity in Z component is not zero, non-zero. So we have to solve this. So we start with, right, angular velocity in Z component is equal to half. Alright, this is V. Remember our V here, the small v here is negative 20 x, y. Alright, and our U here is 20 y squared. So we have small v. We need to differentiate the small v with respect to x. So this is v. Differentiate with respect to x, we will get negative. Amirul Hakim, very fast. 20 y. Very good. So, and then minus. Alright. U with respect to y. So, we go differentiate this with respect to y, become negative 40 y. And we simplify further, negative 20, negative 40 become negative 60 y. Become negative 30 y. Remember, this is basically the step number 1, right? Step number 2 is we need to substitute the point, which is our point. Remember the last point, 1, negative 1, and 2. This is x, this is y, and z. So, angular velocity in z component is negative 30, y refer to negative 1. So, the final answer is 30. So, what's the unit? Remember, this is the rotating, right? So, when it is rotating, radian per second. Okay? So, that is the final answer. So far, do you guys clear on how we solve it step by step? Step number 1, we formulate the angular velocity in x, y, and z direction, and we check whether we have that component. And finally, once we get the angular velocity in z component, we substitute the value of this coordinate, right? Do you have any questions so far? Okay, Christopher, thank you very much. Okay, anyone? Okay, understand. So basically this tutorial to enhance your understanding, right? My objective to help you to enhance your understanding chapter 3. Alright, thank you Atira. Okay, we found the solution A and B. What is this one? The vorticity. Remember the vorticity, the definition is the rate of rotation. The angular velocity is the rotation. This is the rate of rotation. So we need to find the vorticity, right? So from here, remember vorticity is a double from the, by definition, vorticity is a double, a 2 times the angular velocity. So I show you this definition. Right. Okay, this is angular velocity. Okay, this definition of vorticity. Vorticity is measure rate of rotation fluid element as it move. Remember the second term, twice. That means dua kali, alright? 2 times the angular velocity. So our angular velocity previously is omega z. So that means this is the vorticity in z component. In x and y, definitely 0. So we don't consider at all. So from here is 2 times the, remember 2 times the angular velocity. So from here, we get the answer is 60. Okay, this, right, this angular velocity, we have to define its component. Alright, this is vector. Okay, because this is z will refer to the direction of k component. Alright, so the unit is radian per second. Right, so that is very easy. After you get the angular velocity, multiply with 2, you will definitely get the vorticity. Okay, so this is straightforward. So question D, any non-zero rate of strain, right? So you must be want to know what is rate of strain. Remember, the rate of strain is basically the deformation. Remember that once the fluid is in motion, this is fluid, it will either rotate, or it might deform. Ni mata dia. It might deform, or deform can be considered too, stretching and compression. So it might deform. Yeah. So this is the rotation, we refer to the angular velocity and vorticity. The deformation refer to the rate of strain. This is refer to vorticity, and this refer to the rate of strain. Either it is deformed by compressing or expanding. Alright? So, based on our equation previously that we have derived, this is the slide. Alright, this is the slide. Alright, this is the formula. By definition, the rate of strain, alright, tensor. You must be wondering, what is tensor, right? So this is tensor. This arrangement we call as tensor. Tensor, the complete tensor, or we call as a complete arrangement. So this we have the 9 component. You can count 1, 2, 3, and then 3. This is 9 component we call as a tensor. So the rate of strain tensor is the rate of deformation. If AB rotate with angular velocity different from CD, and it produce this formula, which is epsilon xy plane is equal to half partial derivative of v over x plus partial derivative of u plus y, and so on. So based on this formula, we're going to solve this equation, these questions. So the question number D. Alright, remember that the question asks here, and any non-zero. They want the value non-zero rate of strain. That means non-zero epsilon. Okay. So from here, we try to look at the epsilon in xy. Is this 0? Let's take a look. 1 over 2. This is the formula, yeah? V over x plus u over y. Right, this is in terms of xz. 1 over 2 okay, Amirul Hakim. Okay, that one I will clarify later on. Alright, thank you for noticing me about that formula. Because I believe the formula quite lengthy, right? So it's difficult for you to memorize. Our engineering practice, basically we understand, not memorize. Okay. And then y, z. But with the formula given in the test, don't worry, you can Google. I think Amirul, it is open book. So you can Google, you can look at your textbook, then there is the formula. So I believe it is not given. You have to look at on your textbook, because it is open. Compare when you go to the exam, and then the invigilator has to give you the formula. If you do it at home, then you have to prepare. So this one, omega W, omega, this one, this is partial derivative of velocity in z component plus partial derivative v over partial derivative of z component. Alright, let's take a look. Do we have the v component? Yes. We have u component? Yes. X component, y component? Yes. Both of these? Yes. This is non-zero. Alright. This is non-zero. How about this? W totally zero. And z component totally zero. There is no component. So how about this? This is zero. And this is 0 because we don't have k component, right? So we need to solve only this component. Remember that we have the other one. This is in terms of plane, all right? Plane deformation. We have another component in terms of stretching and compression. In terms of x component, y component, and z component. Alright. When we take a look about this, the stretching in terms of x component is u over x. We have, and this one we have, and then this one we don't have, right? So Okay. So when we take a look about this component U, what is our value of U here? Our U component, remember our U component is, remember? Okay, this is U. Our U here is 20y squared. Our V here is negative 20xy. So in terms of this strain deformation, you try to differentiate in terms of U with respect to x, it is 0 because there is no x component. This is constant. So this is 0. Alright. How about y component? This is v with respect to y. So you try to differentiate partial derivative of v with respect to y. So this is v. You try to differentiate in terms of y, you will get the answer is negative 20x. This is definitely 0 because we don't have w component. So how many components that we have? Non-zero. We have 2 components. Alright, epsilon xy and epsilon yy. So yy we have calculated previously, and we need to calculate only this component. So this one equal to 1/2. Alright, partial derivative of v. This is v with respect to x. So you differentiate here with respect to x, you will get negative 20y. And you plus differentiate of u with respect to y. This is u with respect to y. So go the other side, become 40y. And then you try to simplify further, become 20y. And cancel, become ny. Last but not least, you have to substitute the coordinate, which is, remember we have those coordinate 1, negative 1 and 2. So epsilon in xy component is equal to 10 multiplied with y is negative 1. So it is equal to negative 10. Alright, so the unit is radian per second. So what do you understand about negative component, negative value? What happened when it is negative? What happened to the fluid particle? Is it compressed or expand? Please comment there. Is it compressed or expand when the value is negative? Definitely compressed. Remember? Okay. So now you understand, yeah, when the value of the strain negative, it is compressed. And how about the yy component? Negative 20, x is 1. You will get negative 20 radian per second. So both of this strain compress. So it is compressing. Why compressing? Because the angular velocity moving at different direction. Therefore, that is the final answer. So far, do you guys understand? Nurul Jannah, Rio, Christopher, Amirul, Afiq, any one of you? Are you clear how to solve this question to get the epsilon, to get the angular velocity, vorticity, and so on? All right, thank you very much. Okay, so now it is more interesting since you understand well, right? So you can take a look at this. Okay, this is question, this is question 1. Let's move on to question 2. Right. In the question 2, previously we learned about the classification of fluid. We have 1D, we have compressibility, we have viscous, inviscous, we have laminar and turbulence, we have Renault to identify the flow regime, right? So basically the Renault number is very important to know the type of flow, whether laminar or turbulent. Remember, turbulent is the smooth, the orderly manner flow. The turbulent is chaotic flow, fluctuation flow. So Renault number formula given by V refer to velocity, L refer to the characteristic length, and V refer to the kinematic viscosity. When there is the flow over the surface, in natural course, it will happen laminar first. The laminar eventually will become turbulent after go through this transition flow. So we can separate, we have 3 type of flow. Laminar flow is a very smooth flow, orderly manner flow, and transition flow, last but not least, turbulent flow. So this is the critical. Once the flow pass through this Renault number, for the wall pipe, it becomes turbulent. When the flow pass through this Renault number, for parallel pipe, it becomes turbulent, and so on. Now we have question, all right? So the question given, the 2 centimeter diameter, all right, this is pipe of figure below is used to transport water at 20 degrees Celsius. What is the maximum average velocity that may exist in the pipe for which laminar flow is guaranteed? So now they guaranteed that it is laminar, right? So step number 1, you have to imagine that the flow can be categorized into 3 regimes, okay, regimes. So this is laminar, this is transition, that means transition lah di antara laminar and turbulent. This is turbulent, this is in between is transition, right? So based on the basic definition, when the Renault number pass through this point, which is 2000, remember this is, let me copy this. Right. Okay. Okay, sorry. Alright, so this is the wall pipe. This is pipe. So we definitely gonna consider this type of flow because this is rough wall pipe. So the question given, the laminar flow guaranteed. So confirm this is laminar flow. So from here, laminar, transition and turbulent. So basically this one value is critical. Reynolds number critical. This is asterisk. The critical here is around 2000 Reynolds number. So in order for the lamina to convert completely turbulent, it must pass through this Reynolds number. So once the Reynolds number pass the critical Reynolds number, which is more than 2000, that means it will jump, become turbulent. So in order to jump, become turbulent, it must increase the speed from slower speed, increasing to become the maximum. So this one actually the velocity is increasing. Increase. In order to become turbulent, the laminar flow has to increase the velocity. Then it will become turbulent. So what do you think when it reaches the critical Reynolds number? Definitely the velocity will become the maximum. Alright? So okay. So from here, the flow will become maximum. This is the maximum of velocity. So that's why the question given the maximum average velocity, the laminar flow guaranteed. So from here, just about to become turbulent, this is the velocity. So the question asks, find this velocity. Okay. This velocity, the maximum velocity, just about to become turbulent. So we can use this formula. Reynolds number equal to velocity times L. This is characteristic length. Divide with kinematic viscosity. So V is what we need to find. L, characteristic length. This is L. Alright. You might say this is a diameter. Yes, it is the same. Alright. So when you encounter the question, how to find the L, sir? Okay. So the L is always perpendicular to the flow direction. Alright. For example, this is the car. Right. This is the car. Okay. And then this car moving this way. So, what is the L? Can you guess where's the L? Characteristic length. Right, I give you. Is this the L or this is the L? A or B? Please comment there. What is characteristic length for this case? So remember that. Yes, you are correct. The characteristic length is the length perpendicular to the flow. So this is flow. So this is 90 degree. Remember, this is 90 degree. So we call as a characteristic length. So same goes here. This flow like this. So the perpendicular is this. So this is L. So definitely L is diameter. Diameter of the pipe is L refer to 0.2 meter. Remember, convert to SI unit. Alright. Sorry, this is not 0.2. 0.02. Okay. So according to the standard definition, the dynamic viscosity refer to your table, standard table, given by, this is dynamic viscosity referred by the table is 10 the power of negative 6 meter per second. This is given. This is standard kinematic viscosity for air. Alright. So from here, you need to convert velocity become the subject. This is maximum. So Reynolds number critical. In order to become the maximum, we have to substitute the critical Reynolds number multiply with viscosity, then kinematic viscosity over characteristic length. So critical Reynolds number is 2000 and viscosity given here is 10 to the power of negative 6 over characteristic length 0.02. And then you type using your calculator. What's the answer is Vmax. Please help me. What's the answer? Okay, Amirul Hakim, 0.1 meter per second. Remember, the unit is very important. Please specify your unit. Okay. So far, do you guys understand how to solve this question? When the flow is about to reach the turbulent, the flow has to increase the speed. So this is the maximum velocity. So in order to use this velocity maximum, you have to use the Reynolds number at this point, which is referred to the critical Reynolds number. So just substitute the formula Reynolds number equal to VL over dynamic viscosity, kinematic viscosity here. So basically, this is how to answer the question. This is straightforward, very easy. Okay, so far, do you guys want to ask any question? Okay, thank you. Not for now. Okay. So let's take a look about this part. Okay, this one we have found the answer. Remember, the flow consists of incompressible and compressible. Right? This is Mach number. Mach number is the relative flow over speeds of sounds. This is Bernoulli equation. Right? This is important for you to understand. The first term refers to the dynamic pressure, where the pressure is moving. The wind, for example, the wind is moving. So you feel the moving of air. So this is dynamic pressure. This is static pressure. For example, you inside a room, inside your house, you will have the static pressure around you. So this is the pressure due to elevations. Why we have 1 and 2 component? Because we consider 1 to 2 point. Right? So here is the question. All right, let's take a look about this. Right. This is question 3. Right. So the question given, the wind reaches a speed of 144 km per hour in a storm. Calculate the force acting on the window given the dimension in the figure below facing the storm. The window is in the high-rise building, so the wind speed is not reduced due to the ground effect. So given here the density of air 1.27 km per meter cube. So the first step we have to analyze the question. Calculate the force. What is force? The force given here is pressure time area. So calculate the force. Calculate the force. This is the question. Calculate the force. So the force here is force equal to pressure time surface area. So what's the surface area? The surface area of this window. When you look at here, so definitely your area will have this dimension. Right, so that means this is 0.9 meter and this one 1.8 meter. So this is your window. So then the area, you can calculate the area is 1.8 multiplied with 0.9. So what's the answer? The area is, what's the answer? 1 point? Is it 1 point? Yes, correct. 1.62. This is the area. So now you get the area already. Then you need to find the pressure. The pressure acting, which location? This location or this location? So definitely pressure acting in this location. Let's say this is point number 2. And this is point number 1. Alright? The point number 1 and point number 2. Given that this is the flow, when that's the flow, we can apply the Bernoulli equation. So what's the Bernoulli equation? Okay, step number 1. Using the Bernoulli equation, which is velocity squared over 2g multiply with pressure, multiply with pressure 1. I have to delete this one. So using the Bernoulli equation, which is equal to velocity squared over 2g plus pressure 1 over gamma plus h. So this is 1, this is 1, this is 1 equal to velocity 2 over 2g plus p. Wait, I don't know what happened. Okay. Two over gamma plus H2. This is the formula of Bernoulli. Alright. So from here, Okay, nice. And then step number 2, from here, step number 1, you use your Bernoulli equation between 2 points, because we have point number 1, refer to here, this is point number 1 and this is point number 2. So this equation, the left side refer to the point number 1 and this is point number 2. So from here, point number 1, right? Point number 1. So given here, point number 1, the pressure, alright, you can see that the pressure number 1, is the velocity there? Yes, it is given. Alright, is the pressure given here? This is we call as the pressure of atmosphere. When the pressure of atmosphere, we take the gauge pressure, which is equal to 0. So at point 1, pressure number 1 is equal to 0. We use the gauge pressure, because this is under high-rise building. Alright, this is high-rise building, yang paling tinggi lah, bangunan paling tinggi. The building, the top building, it is exposed to the atmosphere. So you can see this is atmosphere. Atmosphere. When the atmosphere, the P gauge is equal to 0, and then the velocity equal to 104 kilometer per hour. Alright, I give you one task. Please convert it to SI unit, which is meter per second. What's the answer? So what's the answer when you convert to meter per second? Afiq convert become 28, become 28. Are you sure? Are you sure your conversion is correct? Okay. So then it is correct. Alright. So you will get 28.89. So I hope you understand how to convert this, right? So for those still not clear or hesitate to do the conversion, please learn it by yourself. You can Google, YouTube, learn how to do the conversion. It's very easy here. Make sure you convert to be SI unit, meter per second. Alright, this is point number 1. And how about point number 2? So let's take a look about point number 2. So the point number 2 is a stagnation pressure. Remember, the stagnation is stack. The pressure, the flow decelerate and suddenly become at rest. So the pressure at the stagnation is higher because it suddenly impact. It becomes stack. So pressure at 2 we call as a stagnation pressure because this is a sudden stop. So pressure 2 is we call as a stagnation pressure. We symbol as PT. The velocity. What is the velocity at 2? Once the flow impact this window, what's the velocity? What do you think? The velocity is it the same with this one? What do you expect the velocity after you hit the car? For example, you drive a car and then you hit a tree. What happened your car? Is it still moving or your car is suddenly stopped? Amirul Hakim, Fikri Ruzilan, is the car moving or stop? Stop. So when it is stopped, that means the velocity is 0. So height, do you think the height is the same? H1 and H2 is the same. So we can say that the height, elevation point 1 and point 2 is the same. So from here, we can cancel which one? We can cancel out this one, 0, because velocity 0. H1 and H2 is the same. So you try to shift the other side, it will cancel. It is not 0, but you cancel it. And then which part? Only left 1, 2, and 3 components. So you only have 3 components. So you rewrite back the Bernoulli equation. Step number 2 is V1 squared over 2G plus P1 rho equal to P2 become stagnation pressure, become PT. Right? PT over gamma. Gamma is rho times gravity. So, okay. So what we have to do? Remember that the pressure, the pressure at 1, P1 is equal to 0. Thank you, Amirul. Pressure 1, this should be cancelled as well. So we leave it only this component, which is equal to PT over rho gravity. So gravity we can cancel out, and we convert the PT become the subject. Alright, PT become the subject, which is rho V1 squared over 2. So density of air given, I think it is given, yes, density of air is 1.27 multiply with velocity is 28.89, the power of 2 over 2. So what's the final answer? Please help me. What's the final answer? Anyone? What did you get? Alright, you just round up 530. Alright? Okay, 530. So the unit is Pascal. Right. I have one comment in your assignment. I sent it to you previously. Please using 2 decimal places. Alright. For example, once you get the answer is 5 to 8.6743, try to use 2 decimal places. 5 to 8.67. Alright. Sometimes I can see that you only use 1 decimal places, you use 3 decimal places, 4 decimal places. So for the better accuracy, right, not the final answer, this is a comment, not yet. So once you do your assignment, your test, please stick to the 2 decimal places. Make it consistent. Whatever your answer, stick it 2 decimal places. Once you write it like this, alright? Because sometimes when I try to mark, there are 4 decimal places, so it make like complicated. So these 2 decimal places is just nice and give you accurate answer. Okay. So you get this one. Remember, step number 3 is you need to find the force. Force equal to pressure time area. So pressure given 530, area that we calculated earlier 1.62. So what's the final answer? Okay. Once you substitute the value, not necessary to put the unit. Alright? Not necessary. Once the final, then you get the unit. So what's the, okay, 585.6, alright, Newton. Right, so that is the final answer. Okay, so far do you guys clear with this? Do you have any question? Okay, thank you, Amirul. Alright, we do the last part before we end up our session. Question 4. Tomorrow is your test, right? Test 1. Okay. Okay, tomorrow good luck and all the best. Basically, your submission of your solution using a Google Drive. Later on, I will post in the group, the Google Drive. You need to submit your solution using Google Drive, not on the e-learning. Alright, so the question given here, sorry, Google Form. Right, confused. Alright, I will give you the link. Submit your solution using Google Form. Your format is in PDF, right? So the static, also the last question, the static pressure head in the air pipe, as shown in this figure, is measured with piezometer as 16 mm of water. A pitot probe indicates 24 mm of water. Calculate the velocity of 20 degrees Celsius of air and also calculate the Mach number, comment the compressibility of the flow. So we have 2 meter, alright? So this is a piezometer and this is a pitot meter, right? So this meter measure the, remember, this meter measure the static pressure. And this meter measure the total pressure. Alright, there are 2 differences between those meter, static pressure and total pressure. Remember that we have learned previously, alright? This one, number 1 measure the static pressure, we call as a piezometer. And the total pressure we measure using the pitot probe meter, used to measure the total pressure. So the question given, we have to analyze the question. Okay, so the question is calculate the velocity. So we highlight, calculate the velocity, calculate the Mach number, and comment the compressibility. So that means comment mean is it compressed or incompressed? Simple. So step number 1. Step number 1. Okay. Apply Bernoulli equation. Please, when you look at there is flow, first using the Bernoulli equation, the flow is in motion. So that means point 1 and point 2 move. Secondly, they are given you 2 points. So definitely using the Bernoulli equation. And then you can see the pressure. So using the Bernoulli equation, Bernoulli equations, V squared 1/2g plus pressure, static pressure here, plus H1 equal to, okay, just write it the same one. And H2. Alright, so let's take a look. Point number 1. Point 1. So what can you say about point 1? What do you see? H1, you can say lah, H1 is equal to H2. So you can cancel. And then the pressure. So is it the pressure given at point 1? The pressure is given. The pressure at 1 is given. Okay. So what's the pressure? How to calculate the pressure at 1? Anyone want to try? Do you have any idea how to calculate the pressure when this is given 16 mm H2O? Do you think, alright, this is special parts where we can see this is H2O, this is water, this is air. You can see, alright, this is air. Alright, yes, correct. Lim, Zin. So the rho, may I know, the rho is the rho of water or rho of air? Lim, rho of water or rho of air? Yes, correct. This is the measure in the water. Given the result is 16 mm. In water here, so we have to use the rho of water. When applied in the Bernoulli equation, this is, you can see this is in air. So we cannot consider as a water. So we apply rho in water, GH. So rho is 9810 multiplied with H. Make sure you convert to SI unit. So become 0.016. So what's the answer? 157 Pascal. Okay. 157, sorry, I try to write it here. 157 Pascal. So, point number 2. What do you know about point number 2? What's the pressure? What is the pressure at point number 2? I mean the static pressure, not the total pressure. This is different, yeah. The total pressure is the combinations of this one. This all term we call as a total pressure. I want the pressure, the static pressure at 2. What's the static pressure at 2? Anyone? The static pressure at 2? So remember that this is pitot tube meter. So when it is pitot, there is a stagnation at this point. Alright. So I try to zoom it. Alright, this is the tube. Basically the tube like this. So this water going this direction, suddenly it will stuck in this point. So this become static. It will be a stagnation here. So pressure at 2 is actually equal to stagnation pressure. Alright, it will stuck at this point. And velocity, what's the velocity at 2? Definitely, when the pressure at the stagnation point, it will decelerate and become 0. Alright. So this velocity M1 that we are looking for. Remember, calculate the velocity. Right, so this one, pressure. Okay. So we try to rearrange the equation. Right, rearrange. Step number 2 is rearrange Bernoulli equation. Velocity 1 per 2g plus pressure 1 over gamma equal to, alright, this velocity cancel out, 0. Only left P T. This is point 2 become point, this is pressure 2 become pressure T, stagnation pressure. Divide with gamma. So far, are you clear? How we get this until step number 2? Okay, thank you. Okay, alright. So the next is, okay. The next is, remember that gamma here is referred to rho time gravity. This term is actually referred to the flow condition. Which medium? Is it in the air or water? Air or water? Please comment there. Air or water in this condition. Previously, we calculate in the water. So in this Bernoulli equation, we apply in the air. Remember, our flow here, condition of flow be in the air, 20 degrees Celsius air. So we have to use the density of air. The density of air at 20 degrees Celsius. So now our part is we need to find the density of air. So using in order to get the density of air at 20 degrees Celsius, we have to use the ideal gas equation. Using ideal gas equation, because this is in air, remember P equal to rho RT. This is considered as air. In order to get the density is equal to P, this is absolute pressure, alright, divide with R times T. This is absolute temperature. When it is absolute, that means we have to plus 273 Kelvin. When this is absolute pressure, we have to use the absolute pressure, which is this pressure is equal to P gauge plus P ATM. This temperature absolute, alright. Sorry. Temperature absolute is equal to 273 Kelvin plus given temperature. Right? R is a gas constant of air, which is 287. Alright? So using the equation of ideal gas equation, density equal to pressure, which is pressure at, you can say that this is pressure at 1. Alright? Pressure at 1 is equal to what we have calculated earlier, 157. This is static pressure, or this is a gauge pressure. We have to plus with atmospheric pressure, which is 101. What's the value of atmospheric pressure? This is as general knowledge. You have to know the atmospheric pressure. 101. What's the value? Can you okay? Is it correct? One atmospheric pressure. What's the value? 101 0.325, right? So okay, wait. The atmospheric pressure, yes, you need to know. The atmospheric pressure is 101.325, right? Divide with R, gas constant 287, multiply with absolute temperature 273 plus this one 20 degrees Celsius. Okay. Okay, it is 287. I think 0.287 is conversion, right? Right? Okay, gas constant 287. All right. So I have checked this one. Can you see? Can you see the slide? The value of R is 287 joule. This is SI unit. The one you mentioned here is not SI unit. It is kJ, kilojoule. Remember, the SI unit is no kilo. It is joule per kilogram Kelvin. So 287. Okay? Alright. So you try to solve it. What's the final answer for density? Try to help me. What did you get? Amirul Hakim? What's the density of air at 20 degrees Celsius? Okay, 1 point. Okay, 1.21. Okay, correct. Okay, make it constant. You try to use 2 decimal places to 1. Okay, kilogram per meter cubic. So in order to get the velocity, step number 3. Now we go to the final part. In order to get the velocity using the rearrange equation, this is the velocity, right? Velocity we need to find over 2g plus pressure at 1. What is the pressure at 1? 1. Remember, this is not absolute. You have to use the gauge pressure, P gauge. This is the one that you get earlier. 157 over right, rho g. You can expand or you can like this, equal to PT over okay, PT over over gamma. Okay, so let's try to rearrange the equation. So what did you get? The last part. Wait for a while, yeah. Okay. So from here, you try to rearrange the equation. Okay. You will get V1 is equal to, okay, 2 row of air. This is actually PT minus with P1. Alright. Stagnation pressure here, basically you can get directly from here. Alright, the stagnation pressure. So the stagnation pressure is like we have done earlier. PT equal to rho GH. Okay, so PT is equal to rho G of water, which is water is 24. So rho G is 9810. The distance here is 0.024. So what's the answer there? 9810 multiply with 0.024. 235. 235.44 Pascal. Alright. So from here, okay. So from here, I think it is easier for you now to substitute the value. So substitute all the values. Alright, V1 is equal to density of air, which is 1.21 PT. Alright, this is atmospheric pressure. Okay, wait here. So what's the PT given here? We have calculate, which is 235.44 minus with pressure at 1. We have calculated previously. Let's take a look. Which one? This one, 157. So 157. So can any one of you please give me the final answer? What's the final answer? The velocity? Okay, correct. It is the same with the solution manual. Alright. 11 point. Is it the same? Yes. 39 meter per second. So therefore, this is the final answer. So basically 3 steps. Using the Bernoulli equation, identify point number 1 and point number 2. And rearrange the equation after we have simplified. And find the pressure 1 and a static pressure. So you can actually find the static pressure at 1 directly from piezometer, and the static pressure, this is a stagnation pressure at pitot tube pressure using rho GH. And finally, you rearrange the velocity become the subject. Is a square root 2 over density of air, PT minus P1. So this one you get it from this equation. So that is the final answer. So far, do you guys understand on how to get the value all this value from step number 1, 2 and 3.
Doktor,
Hmm.
I have a question. Kenapa dekat bawah P1 tu apa ni lambda dia tu kita guna yang 1.2, kita tak guna lambda untuk water.
Mana satu? Yang ni ke?
Yang tu. Kenapa kita guna 1.2 sama dengan yang dekat yang 2 ni?
One in the air. Yes. Okay. Alright. So sekarang ni dia ada dua case. Fikri. Case, okay, cuba baca balik case dia. A static pressure heat in the air. Okay, dia kata static pressure heat in the air pipe shown is measured with piezometer as 16 mm of water. That means this one dia nak bagi tahu value of P1 using the
Piezometer.
using the piezometer in the water. Tetapi kat sini actually the flow is in the air. Nampak tak? Nampak tak dia punya, alright. Okay, piezometer ni dia punya reference dia kat mana? Adakah dekat air ke dekat water?
Piezometer ni dekat reference dia dekat water yang atas tu.
Okay, nampak H2O kan? So, pressure kat sini, okay, pressure kat sini kita kena guna reference dekat water, which is nampak tak kita punya formula rho GH mana tadi?
9810 tu.
Nampak tak kita guna water sebab kalau kat sini bagi mercury for example, mercury kita kena guna density of mercury. Tetapi flow yang kat sini is in the air. Faham tak?
Faham.
So bila flow dekat air, kita kena guna Bernoulli Equation under air, which is air. Nampak tak kat sini? Reference dia apa? Water ke air? H2O ni?
H2O tu water untuk yang piezometer, tapi untuk pressure saja.
Yes, untuk pressure sahaja. So kita guna reference refer to water. Kalau reference to refer to mercury, and then we have to use the mercury punya density in order to get pressure. So it refer to reference dulu. Tapi the flow dalam ni is air. Nampak tak dia dah mention bulat-bulat kat sini? Plenty air.
Masih ada.
Okay. Okay, Fikri asked the good question. Basically, I try to solve this question. When I refer back, this is a reference from the water, then we use the density of water. Tetapi, dia punya flow, kita kena lihat, it is in the air. So, we use the Bernoulli equation in the air. Nampak tak saya buat ni? Rearrange Bernoulli equation, is it in the air or in the water? So, definitely it is air. So, kita kena gunalah, we have to use the gamma in the air, and then everything in the air, the density in the air. Only the pressure je kita perlu dapat daripada reference water. So the rest will be in the air.
That's okay.
Okay. Okay, thank you Goziji, Amirul, thank you very much for your feedback. Right. So basically that's all about chapter number 3. It is easy, right? Chapter 3, you learn the Bernoulli equation, the angular velocity, using the formula. It is straightforward. So we have covered everything about the tutorial 3, and please do yourself study chapter this one later on, because tomorrow is your test 1. Try to work out on another example. And once you try to solve, you get the answer, it will be interesting later on. So never mind, this one I will post in the e-learning, this video recording, and then you can revise later on. So I hope that you okay go ZG. Anyone have you scanned the QR code? Right, let me scan the QR codes kehadiran. So you under section GoZG under section 21 or 22? Under section 21 or 22 go? 21. Alright. Okay. Okay, I send to WhatsApp. Okay, later on I send to WhatsApp. I hope that next week is the semester break, right? So use your time. I advise you use your time well. Enjoy yourself. Okay. So we meet on the second week next 2 week. Okay. So good luck and all the best for your test tomorrow. Right. Okay, thank you everyone who actively participate. Okay, Zara, thank you. Okay, everyone, thank you. Bye.
Thank you, Doctor.
Okay, thank you.
Thank you, Doctor.
Okay.
Assalamualaikum.
Waalaikumsalam, Amirul.